Welcome to Brain Vision.
Okay, so let's quickly calculate the final temperature between the body temperature of a man, which is, let's say T subscript M, which is 37 degrees Celsius. That's the body temperature of a normal human being. And then the temperature of the drink he took is 12 degrees Celsius. All right. Now, since the body temperatures are different, there will be a transfer of thermal energy. Okay, so the heat lost by a man is equal to heat gained by drink. Heat gained by drink. Now, energy is conserved, so we need to take note of that, assuming that no temperature is transferred to the surrounding. So the heat lost by man is equal to the heat gained by the drink. Good. Now, the mass of the man is 70. Mass of man is 70. Mass of the man is 70. How do we calculate for the mass of the drink he consumed? How do we calculate for the mass of the drink he consumed? All right, don't forget mass is equal to density rho times the volume. Now, the volume of the drink is 0.355 liters. If you convert this to meter cube, this should give you about 0.00355 meter cube. Let me rewrite this. 0.00035 meter cube. Okay. All right. So that is the volume of what the soft drink you took. So to calculate the mass of the drink as at this volume, we use this formula. We know that the density of water is 1,000, and obviously the drink, let's say, absolutely made out of pure water or total water. All right, we will say that the mass is equal to 1,000, which is the density of water multiplied by the volume, which is 0.00035 meter cube. So when you do that, the mass should give you 0.355 kilograms. So this is the mass of the drink that he consumed. Okay, so we are going to use the equation for the heat energy. So we have the heat lost by man, mc delta T, is equal to the heat gain, let's say negative. Okay, since he lost heat, it has to be negative. And then as the drink gains it, it's positive. So mc delta T. Okay, all right. So let's go on to look at that. So the mass of the man is 70 multiplied by his specific heat capacity, is 3,480, into bracket 37 minus the final temperature we are supposed to calculate, their equilibrium temperature. That's the final temperature, times the mass is equal to the mass of the drink, 0.355 multiplied by the specific heat capacity of water, let's say 4,200, okay, into bracket the temperature change minus 12. Okay, all right. So when we do this, we get negative 2.43600 TF, okay, plus 901.3200, which is equal to, if we evaluate the other side, we'll get, if we evaluate the other side, we'll get 1.489.5 TF minus 178744. Okay, all right. Now, when you evaluate all of this, it should give you 9013200 plus 1717874.1. Sorry, this value is 17874.1. Sorry, not 44.1. All right, so let's move on. So this is equal to, we are just grouping the TFs at one side and grouping the constants at the other side. So this should give us equal to this should give us equal to 2450 5089. Okay, TF. Now, when I group all the TFs at one side of the equal to sign, this is what you get. If you group all the TFs at one side, that is what you get. So we will say that TF, which is the final temperature or the equilibrium temperature, is equal to 9031074.1, all divided by this value. Okay, all divided by this, which is 245089. Okay, so when you do that, we have TF being equal to 36.85 degrees Celsius. So this is the final temperature as a result of the transfer of heat from the body of the man to the drink he took. So that was the final temperature that the body attains. Now, this temperature, it's more obvious and should be taken into consideration. Now, it's about, let's say, 37 minus 3, 6.85. Okay, that's 37 minus 3, 6.85, which has a difference of about 0.15 degrees Celsius. Okay, now this temperature is a temperature that we can't ignore because most temperatures have a least count of about 0.1. Most temperatures that use at the hospitals. So a temperature of 0.1 shouldn't be ignored since it's the least temperature. Okay, so we can say 0.15, approximately 0.2 shouldn't be ignored. So it should be taken into consideration. Okay,